Okay. Next up, we have Martin Mouth from Uber. Where's Martin at? There he is. Thanks. I know, he wasn't in the room. Yeah.
Oh, there's already one of these.
Yes.
Excellent.
Yeah.
Testing. Can everyone hear me? Testing. Testing.
No good?
Testing.
Yeah. If it doesn't work, I'll just give you this guy.
Switch it out. Thank you. Testing. Okay.
Yeah, much better. I'm excited for some compare and contrast here. We just heard about how to generate data at scale very quickly, and now we're going to hear about what do you do with that data at scale
That's
very
half
quickly.
the problem.
All right, let's hear it up. Give it up for Martin.
So yeah, my name is Martin. I manage the metrics team at Uber, where we work on the open source metrics platform, M3. And yeah, here today I'm here to talk to you about how to query millions of time series, hopefully efficiently. So the agenda today, hopefully I can convince you first that it's a legitimate problem that we have to solve before looking at some of the various solutions that are available. And then everything I'm going to be talking about today is open source, so there's some links to stuff that you can try out today. Cool. So do we really need to query a million time series? Is it a real problem? So I hope you're all familiar with Uber, the product. This is not real production code, but let's pretend we had a function called request car, and we're trying to just emit a metric to figure out what the latency of that one function is, right? By the way, this is my really bad Go code. I don't write code these days. For this one metric, we're trying to, we're using a histogram because histograms are better than summaries. And we're putting just 5 tags onto it, right? City, product, status, OS, and version. Does anyone here want to have a guess at how many time series that single line of code can produce? 100 million, that's a great guess. It's more than a million, which is good, otherwise this talk would be very boring. It's not quite 100 million, but let's go to the next slide. So for every one of these tags, there are multiple tag values, of course, and then for every unique tag value, you result in a new time series. So for cities, we operate in about 400 cities or so. For products, this is like UberX, Uber Pool, and whatnot. We have about 10 products. Status codes, think like HTTP status codes, probably like 10 of those. OS, let's just pretend there's 2, no BlackBerry app. App version, let's say conservative estimate, there's like 2 versions per OS or something like that. And then we are using a histogram here. So for histograms, you need buckets, right, to put the values of your histogram in. Let's just say by default there are 10 buckets. So with these cardinalities, which are all pretty conservative estimates, you actually get 3.2 million time series produced by that one line of code, right? And that's just those 5 tags. We haven't added things that are pretty common, like the environment, production, dev, et cetera, the pod, the zone, the region that you're running in, or even my favorite one from engineers are the host, right? People love putting the host or the instance tag on it. So imagine multiplying those by 3.2 million, you're going to get a way more time series. Cool. So it's definitely easily possible to write a line of code that produces a lot of time series. Is it really that useful? Is there really a use case where you need to query all million of those, right? So this is actually a graph we have in production today by somebody. They've literally just plotted their million time series. It's not super useful. I love the description just called count. And actually, the y-axis is exponential, which is fantastic. So if you just plot a million time series, maybe you can't really make that much sense from it on a graph. But there are actually legitimate query use cases, right? So I've listed 3 here. Even if you're just the developer of that endpoint that we looked at earlier, and you just want to know the overall P99 latency of that one function, you actually need all 3.2 million time series to go get your overall P99, right? If you're a mobile engineer and you want to slice and dice by the OS or the version, or you're a city operations person, you want to break it down by city or product, no matter what sort of grouping you want to do, you sort of still need the underlying 3.2 million time series. And as a developer, they don't quite always understand why it takes so long, because if I just want one latency, all I really want is 400 pixels on a graph somewhere. Why is it taking so long? Or if it's not taking so long, why does it error out, right? So the reason is a million time series is actually really expensive. So if we do the maths here, each data point so this is just for 1 million, not for 3.2 million. Each data point uncompressed is 16 bytes. You need 8 bytes for the timestamp, 8 bytes for the value. And when you have a million series, let's just say for a whole day, you want a million series at 10-second resolution, which seems pretty reasonable, or a week at 1-minute resolution. You're really going to be using 150 gigs of memory just to store that before you do any operations on it, right? At Uber, we serve about 2,500 queries a second. Some of them go up to 35 days of data at 1 minute. So not only do we constantly need more and more machines in our query tier to sort of hold all this stuff, but we're actually running in or hitting the limitations of a single machine as well, right? We can't store all of this data in the memory of one machine. And of course, our query nodes all the time. This is a pretty common problem for us. So when we go back to the developer and explain all this to them and say, hey, this is actually what you're really doing underneath the covers, it's actually millions of time series, it's quite expensive, we can help them work through the problem, which this is what we used to do. We can sort of tell them that, hey, emit your original time series because you want all the dimensions on it, because you want to drill down, because at debug time you don't know what you might need. But also, for every view that you want in aggregate, you can emit a second metric that doesn't have all the dimensions that that aggregate doesn't need, right? This is one way to get around the problem. So you can see here, for the 3 use cases I put up earlier, we're just emitting 2 more metrics without all the other tags. And here you also notice that I'll probably have to change the name of the metric. So it's latency by version or latency by city, so that I don't have a namespace clash or something like that, right? So this is possible, but it's quite annoying to do this, right? Every time you need a new aggregate view, the developer needs to go back to the code, write another line of code, deploy. This information is not backfilled or anything like that. And sometimes not even the developer, right? A operations person will come and want a different view, and the dev has to go and push that out. So it's a really annoying experience, but they can get around the problem. A much happier developer would be back to the first case, where you just emit a line of code with all the dimensions they need, and they push the hard part of the problem to the observability team, right? This is our job. Even happier than that is, maybe they don't even need to put all the tags on it. Maybe we can just grab the tags from the context automatically for them, right? Which will make things easier. Or even better than that, maybe the RPC framework that they're using can just emit the latency metric of their endpoint for them, right? They don't even need to write any line of code. So the point here is that, we should really try to avoid overloading developers with the implementation details or the deep knowledge of the dependencies that they need to use, right? Every developer needs a metrics. Every developer needs alerts. They need logs. We don't really want to push the knowledge and the difficult parts of it to them. We want to make it as easy as possible and sort of give them a magical experience, and also take care of the hard stuff ourselves, I guess. So when it comes to millions of time series, there's 2 parts of the problem. The first part is how to ingest, index, and store them efficiently. And we've given a lot of talks about this, so I won't dive into that part of the problem, but there are links there. The slides are online. The second part of the problem is, once they are stored and indexed, how do you quickly and efficiently query them without asking the devs to make any code changes or things like that? So that's what this talk is going to be about. So the first thing that I want to dive into is having more efficient query engines. So your query engine is responsible for making these queries. If we make them more efficient, maybe we can solve the problem. So here we have the steps of a basic query engine. This was our basic query engine. This is how it worked. You see a fetch statement here. By the way, this query language is M3QL. It's our own sort of in-house Uber query language. We will be open sourcing this in a couple of months. Sort of tag-based, has pipes into functions and whatnot. It reads left to right. So in that function here, we want to fetch the request count for 3 particular cities. We want to figure out what the per second rate is, and then we want to sum everything up, right? So a basic query engine will take the functions from the fetch statement, so separate the two out, right? It would send the fetch statement down to your storage nodes to retrieve all of the time series data that you need. And then once you have all the time series data back in the query node, then you apply the functions from left to right, and then you send the results back to the user, right? This is like essentially the logic of a basic query engine. This was the first query engine that we implemented, and it was better than Graphite Web for sure, but it had some bottlenecks. So the bottlenecks are in memory, compute, and network. So for memory, of course, as I mentioned earlier, just keeping the raw time series in memory takes up, in memory takes up a lot of memory, right? 150 gigs of memory. If you want to do any sort of grouping or aggregation, that takes even more. The computation required for each function is a lot. So if you have like 3 functions that you want to apply, that's 3 computations you have to perform per data point, not per time series, right? So when a million time series, each of them have thousands of data points, you're doing billions and billions of computations. So that's quite expensive. And then of course, network sort of goes hand in hand with memory. If you have 156 gigs of raw data in memory, you had to get it there somehow over the network. That's transferring 150 gigs over network, especially if you're going cross-region or cross-zone, is also quite expensive. Cool. So this is the first thing we did with our new query engine to sort of try to optimize this, right? So this is only the fetch part of the problem, so we've ignored the functions for now. So if we're fetching this from our storage, we sort of break our fetch up into multiple blocks, right? So here, for this example, we want to fetch data between timestamps T1 and T30, and we've broken up this query into 3 blocks between T1, T10, et cetera, right? And then we make these fetches down to the storage at the same time. So you're going to reduce sort of P99 latency if you do that in parallel. And actually, we don't even wait for all the data to come back. So as soon as one block of data comes back, we can start the function processing there, right? Because what we found is that a lot of the functions that you apply, you're actually applying across the time series in a vertical function, as opposed to along the time series in a horizontal, right? So as soon as they come back, we can start applying the functions, which is nice. And then also for every block that we fetch for every time series, we actually fetch that compressed, right? So modern day time series databases, they all do compression on their time series data. So rather than having the storage return you uncompressed data, which is uses a lot of memory, we actually want to have it returned in the compressed format, right? So a lot of modern day time series databases use like TSZ encoding from Facebook's Gorilla paper. We do the same thing in our time series database. We use a variant of that gives us about an 11x compression ratio, right? So just by doing that, your raw data that you need in memory is 11x better. So that 150 gigs gets down to like 13, 14 gigs of memory required, right? The other thing, optimization that you can do here is if you think about a time series database as well, they actually store their compressed data in blocks in a similar fashion, right? Because everything is sort of time-based, and you sort of want to expire data over time. So you sort of want to drop blocks at a particular, after a particular time. So what you'll find is that a lot of time series databases will keep blocks of data like maybe 2 to 4 hours in width. And if you actually match that 2 to 4 hour width with your query engine, if you think about that, the query will now literally go down to the time series database node, grab that 2-hour block straight from disk, or if it's already in memory, and just ship that all the way back to you. The data node doesn't need to do any stitching of the data for you, right? So that's pretty optimal. My laptop turned off. Okay, cool. So the next thing we do is sort of just-in-time decompression and lazy function evaluation. So I'll talk about the just-in-time decompression first. So as I mentioned earlier, all the blocks are compressed. We only actually decompress the values as we need the next value. We only decompress as we need the next value to figure out our functions. So if you do this and you don't decompress the whole thing, you don't actually need to allocate all of the memory for all of your time series. You, of course, still need to allocate all of the memory for your result series, but that's not as much, right? So here, as we get to T1, we only decompress the next data point, and then we apply the functions at that point, right? Before diving into the functions, I do want to mention here that, depending on your time series database, if you do one that does quorum reads, we actually don't do the quorum at the storage node side because, again, you have to decompress everything. We actually ship all 3 replicas back into the query engine memory, and then we do the quorum read as we're doing the decompression at the same time. So that's why there's 3 copies there for the compressed blocks. And then we also do lazy function evaluation. So the traditional query engine would do the functions left to right. They'll do a scale to seconds horizontally across all of your individual time series. And then you do a sum where you go through, again, all of your time series, and you sort of sum each data point up vertically, right? That's quite expensive, requires a lot of computations. So we can actually do for transformation functions like scale to seconds, we'll actually lazily evaluate that after the sum. Right? So in that sense, we'll actually sum up the 3 values at T1 first, so you end up with 1 value in the result, and then we'll scale that to seconds. So if you're doing that, you're still doing the sum across the time series, of course, you can't avoid that. But now you're only applying the scale to seconds to 1 value, as opposed to 3 values or 1,000,000 values for your time series, right? These are just a few of the functions in our new query engine. We actually just dropped a blog post this morning about it, so you can figure out all the other cool things that we do. But what is the result of doing such a thing, right? So for example, if you're fetching 1,000,000 time series, going back to that example, and you're applying, let's say, 3 transformation functions and an average to it, right? So these functions essentially convert the value to a percentage, and you want to figure out what your average is across your fleet or something like that. So for 1,000,000 time series, again, for 1 day at 10-second resolution or 7 days at a 1-minute resolution, unoptimized, you're using 150 gigs of memory and network, right? And you're doing about 60 billion computations across all of those data points. In the optimized version, using the features that I just talked about, you can get that down to about 40 gigs because everything's compressed. It's not quite 13 to 14 in this example because we're fetching back 3 replicas, but if you didn't want to fetch back 3 replicas, you want to do eventual consistency, you can get that down to like 13, 14 gigs, which is pretty nice. And then the computations is a huge saving, right? Because we're applying the average first and then applying the transformations. So it goes down to 50,000 computations as opposed to 30 billion. So this is pretty good. You're still using 40 gigs of memory in the worst case for a lot of your queries. And if you're doing thousands and thousands of queries, you're still probably going to get booming nodes. So there are other things that we can do as well. The next thing that I want to talk about is distributed queries. So the idea behind distributed queries is that you want to push as much of the query computation down to the data nodes as possible, and this should, in theory, reduce the network bandwidth, also distribute the memory and CPU resources, because all the nodes are sharing the work, right? You're distributing the work. So if we look at an example of how this works, I have either my query server or my coordinator node or one of the data nodes down here doing the coordination. I have a particular fetch statement that matches all of these time series that are on each of the time series database nodes, and I want to apply a sum. Right? So instead of fetching all the data back like we would used to, we would actually push that sum function down to each of the data nodes themselves. Each of the data nodes will apply the sum to all the time series that match that fetch, and then you'll return each of the small sums back into the coordinator or the query server, and it would perform the sum back up to the result. Right? This works pretty well on eventually consistent systems, and by eventually consistent, this is like a design of something like Influx, where you have 2 replicas. When you read, you hit a load balancer, you get the results of one, either replica, and then within one replica, you can do this fan out and distribution of the function and whatnot. And then on the right side, there's also like a load balancer, and it goes to one of the replicas, and one replica is responsible for replicating to the other one. So if you have a system like this, this distributed query works out pretty well. If you want a strongly consistent system and you want to do quorum writes and quorum reads, this distributed query is much harder. And I'll go into that in a second, but just a quick slide on why Uber really went for this strong, consistent reads and writes. We actually had eventually consistent system back in 2015 to 16, where we used Cassandra with RF2 and hinted handoffs, and our developers complained a lot about that system, right? Like things were flaky depending on which replica you hit. The hinted handoff queue had a limited capacity. As soon as it was over capacity, you would lose data at that point, and then you would have to do a repair across your whole cluster, which was not really feasible. And at our load, we couldn't really go up to RF3. So when we designed our own time series database, M3DB, we actually made strong, consistent quorum reads and writes a requirement for us, right? And in a system where you're doing quorum reads and writes, this distribution is now sort of actually almost impossible now. So in this design, in this diagram, it's a little bit different. You have the replicas of the time series on each node. There's 3 replicas in this cluster, and all of the time series you see has some gaps, right? Which is actually fine because quorum, you just need 2 out of the 3 writes to succeed. So for every data point, as long as we have 2 copies of the data here, it's a successful quorum write, and we can get quorum reads on the way out. So you see there's some missing gaps there, but if we tried to do the same trick and distribute the query, and you tried to sum up the results of each replica first, and then perform the quorum on the summed up things, you can't actually do it, right? So in this particular example down here, you'll see that my individual sums for each replica is different. And when you have 3 different values, you can't actually get quorum, like averaging or something like that is not an accurate answer, right? So that's an issue. The second issue is that this is if your database was designed to have all of the time series on each replica on the same nodes. If you did something like that, you'll probably be susceptible to like hotspotting and things like that. So generally, a lot of time series databases will use vnodes, right? They'll spread their shards or they'll spread their time series databases across multiple nodes. Each one, there's still 3 replicas, but you don't know which one they're on. And in this scenario, you can see again here, you can't really do summing on each individual node, right? Because even the time series on each node is different, right? So this model doesn't quite work for sort of more strongly consistent systems. There's also some other separation of concerns here as well with this model, like your database, your time series database nodes are already doing reads and writes, and a lot of them, right? So adding additional aggregation logic to them, will use even more resources, right? Like performing the aggregation will use more resources for sure. Every time you want to perform an aggregation, you got to remember all the data on the time series database is all compressed. So to perform an aggregation, you got to decompress that data and then maybe compress it again later on. So that uses even more resources, right? And of course, this will lower the risk of ooming your stateless query nodes, which is great, but at the cost of like higher risk of ooming your stateful database nodes, right? And that is a huge risk. If you lose 2 nodes, you lose data at that point. You can't do writes at that point, right? So for us, we'd much rather risk our stateless query nodes, and at the same time, it's also much easier to scale up the stateless query nodes. So even if they oom, you're in a situation you can just throw a whole bunch more nodes into a cluster because they're pretty stateless, right? For database nodes, it's much harder to throw 10 nodes in. Each node has to take over shards. You have to transfer data. Everything's stateful. It's much harder. So while we don't do distributed queries for our real-time dashboards or alerts, there is a time and a place for them, right? So we have use cases here in Uber where you might not need to aggregate all of the time series you're looking for down to 1. So as an example here is like, we have sort of a capacity planning use cases where we want to fetch the core usage for every core in our cluster and like sort of map that to services or something like that. And to fulfill a query like that, we actually leverage a generic distributed query engine called Presto. So Presto will sort of distribute a query across multiple nodes, but they're not down in your data nodes. They're in the Presto query nodes, right? All you have to provide is a connector so that it knows how, in its query language, which is SQL, it knows how to access the data from your database. And providing a connector is much easier than writing a whole query engine for sure. It has sort of paging built in, which is nice, right? So there's not a single node that needs to hold all of your results for the whole time. You can page through that. Whereas, if you think about a lot of metrics clients like, Grafana or alerting engines, they don't really have paging built in, right? So that's sort of nice. And then even better than that is, and this is the biggest pro to us, is it really allows you to now combine your time series data with all of the other data in all of your other data sources, right? Or your databases in your company. So connectors exist for Cassandra, Hive, Kafka, MySQL, etc. So now what you can do is in a single SQL query, you can take data from your time series database and combine that and do joins against your table in Cassandra or your MySQL table, right? And that's a huge benefit, right? It really means that you need to embed like less information in your metric tags. You actually need to put less dimensionality into your tags, right? The con of this is, of course, it's not as efficient because it's a generic query engine. It's not quite as efficient as building, a query engine optimized for time series data because it's not optimized for time series data. But it doesn't actually need to be, right? A lot of these use cases that people use it for are analytical use cases where, it can be okay to wait like 30 seconds or a few minutes to get your results. Cool. The last approach I'm going to be talking about is aggregation on ingestion. And aggregation or ingestion is the idea that, if you have a query that you frequently execute and it's resource intensive, you want to just do that ahead of time and store the results into a separate time series and then query that separate time series that's already aggregated and rolled up. So for those who are familiar with Prometheus, this is how Prometheus recording rules works, right? So you have a prom instance there that's scraping metrics from a whole bunch of prom endpoints, and then you define a recording rule. And what this recording rule does is you give it a promql expression, and periodically, you define the interval. It will run that expression, get the results, and store it as a new time series on that single node, right? This works great when it's one node. When you get to two nodes, or when you get beyond a single Prometheus node, you probably need to shard the endpoints between the two instances. You're probably running the rollup rules on each instance, and then you probably need to do some federation between them, right? This is how you scale up Prometheus. It might be okay for like, two sort of instances. As you get up to like the hundreds of Prometheus instances, it really becomes pretty unmanageable pretty quickly. I don't know of any company that has done this well thus far. At Uber, for our use case, we have single services that expose more than 800 million metrics, right? And I think like one Prometheus node right now can handle about 1 million metrics. So we'll need 800 Prometheus instances, plus another 800 more for high availability, and just for that one service, right? And we have hundreds of services that emit more than 1 million. So you have to do the sharding across a lot of services. As you saw earlier, with one line of code, you can emit millions of metrics. So this is quite an easy situation to get yourself into. The services also run on a compute platform, so they're rescheduling all the time, right? So it makes the problem, the discovery problem, the tracking problem even harder, because it's constantly changing. And the other pain point about the recording rules that we don't really like so much is that the recording rule itself is local file-based. So you'll need to create a local file for your local Prometheus instance, and that's how you define your recording rules, right? So when you have hundreds of Prometheus instances, I don't know of a great way to sort of like push out all of these files instantly across a cluster, right? If you're using something like Puppet to do that, it's going to take a while. And if that's the case, you're not going to get those rules across the cluster at the same time. Your values might be off. The other thing is the high availability model of Prometheus is I sort of like have two instances. Either can alert, you're not really, they don't really sort of like, what's the word I'm looking for? I don't really like merge or can't really do like a quorum read or anything between them. Cool. So at Uber, we approach this problem in a slightly different way. We actually have an agent that runs on every host. This agent is called the collector. This agent is responsible for scraping all of the Prometheus endpoints that's exposed by that one host, right? So it doesn't really do it remotely. You see in this example, there's also some clients that push to that agent. So at Uber, we still have to support statsd, carbon formats, all of the legacy stuff. So for all those clients, and also if you want to use a tagged client that's push-based, because a whole bunch of use cases where push is better than pull, they all get pushed to the same agent that's on the host. You sort of solve the discovery problem. You only need to know what port the agent on the host is looking on. And then we have a central aggregation tier, actually, called R2. That's that thing in the green on the right. And then we have a sort of strongly consistent key value store backed by etcd, which actually stores all of the mapping and the rollup rules, right? So I'll talk about the rollup rules first. I'll go into the mapping rules. So all of the agents on every host go and read etcd for all of the rules that need to apply, right? Let's have a look at the top collector for now. So the top collector will get a metric that matches a few of these rules, right? It will match a rollup rule. So it will put it in the appropriate entry at the top there in R2. And that particular metric also needs to sort of be persisted by itself. So at the same time, it would also write that metric. Let's say this ID of this metric is T2. It also write the metric into its own separate entry in the aggregation tier, right? Same thing with this collector at the bottom. It will get a different metric, TS1. Let's pretend that it matched the same rollup rule. So it would also put that value into the same entry, the rollup entry. And then you can see here in this example that TS1 is actually, there's two entries for TS1 in the R2 tier, but they're at different resolutions, right? One is aggregating at a 10-second resolution, and one is aggregating at a 1-hour resolution. So those are the sort of rules that you can put in etcd. They're called the mapping rules for like how granular you want this data, right? And then you can imagine that, well, not imagine, but periodically, when the time is right, when you have the whole hour tile or you have the whole 10-second tile, that data gets flushed into our persistent time series database. And the beauty of this is like, for the rollup rules, you now don't need to run the query against your time series database, right? You already have it like formed at aggregation time, right? You don't need to constantly read and write back into your TSDB. Same thing with the individual time series, right? So a lot of time series databases out there, to generate like a 1-minute tile from your 10-second tile, there's some background job that comes and reads your 10-second tiles and converts them to 1-minute tiles. So you're constantly reading and writing your data to and from your time series database, right? And that's a performance hit for sure, and also complexity as well. So we avoid all of that. Everything is aggregated in a central aggregation tier, and it just gets written into the time series database, right? And when you do reads, they're just serving queries. Cool. So some advantage of this, it's highly scalable. The nodes own particular shards. You can add a new node. It will sort of take over shards. There's a global consistent topology that's backed up by etc.d. Sort of highly available and reliable. There's multiple replicas, and between the slave and the master, they do etc.d backed leader election. So the slave will make sure that the master is flushing the correct tiles to the backend, and if not, it will take over. And then there's as I mentioned earlier, there's a centralized, consistent view of the rules, right? Like all the rules are in etc.d. They're not on a file somewhere on a host. And those changes, when you make an etc.d change and you have a watch on it, those changes go out instantly. So all the agents on every host can apply the same rule at the same time. Slightly more efficient because you're not constantly having to read all the metrics for the rollup rules and read all the metrics to generate your larger tiles and whatnot. And then I do have to point out here, though, is that we only perform this on aggregation functions, right? So you can sum, average, and things like that. We don't actually apply transformation functions at the aggregation tier, right? I mean, it's an aggregation tier. The reason why we don't do it is, and it's a bit different to Prometheus, the reason why we don't do it is that we found, and as I shown in the query engine earlier, we can actually collapse the transformation functions down to like a single step, right? And once you've already got all the time series aggregated, you're really only talking about a few time series. Now, when you're applying like, the 3 transformation functions at the same time to those few time series, it's actually really quick. So there's no need for us to introduce additional sort of complexity into our aggregation tier and apply transformations there. They only take care of the aggregations. Cool. So devs can sort of solve the problem now. We've given them all of the tools that they need, right? So this is a picture of the landscape right now of the tools available to them. The stuff in green is the stuff we've written as part of the M3 metrics platform, but it's mix and match. You can use Prometheus, recording rules. You can use Influx. There's the Flux query engine that have a lot of the optimizations as well. So there's a lot of tools for developers to sort of solve this problem of querying a lot of metrics, but they don't use them, right? So what we found at Uber is that only 1% of the services at Uber actually use custom aggregation rules, right? And the reason is that the typical flow of the developer is that they'll emit millions of metrics. They'll attempt to graph millions of metrics. They'll probably be blocked by the query engine. We'll probably send back an error. Then they'll go back and go, oh, they understand the problem. Then they learn about R2 and the tools available. And then they go and dynamically create the rule. So at least they're dynamically creating the rule. They don't have to like deploy code again, which is a help. But then that rule creates a brand new time series. Then they have to go back to their dashboard and query for that new time series, right? So it's a pretty manual, tedious path. And if you're not querying that many time series and you don't get blocked, you never know that this exists. So the folks who are maybe querying hundreds of thousands of time series, they don't run into this problem. They just don't make their queries optimal at all. So what we found was that there was less ooming for sure, but there was still a lot of ooming in our query nodes because only 1% of folks were leveraging this. So where we really want to get to sort of in the future, and we're starting to get there now, is a way where devs don't have to manually create this, right? So imagine a flow where you just emit all the metrics that you need with all the cardinality. You create your expensive query and you create your expensive dashboard. And when you do that, we automatically go and create the rollup rule for you, right, behind the scenes. And then we backfill all of the data for you. And then we make sure that the query engine knows what the new name of the new time series is, and it plugs that into the graph for you, right? So you just come up with your expensive query, and behind the scenes, everything is being magically done for you. And you don't know that you're not actually aggregating those millions and millions of time series. So it's like hopefully a magical experience. Cool. So where can I get this stuff? For query engines, as I've been talking about the M3 query engine, the Flux query engine also has a lot of these functions in there. It's pretty cool. We just dropped a blog post, as I mentioned earlier today, so there's links to the code and the blog post. There's a link to the Presto distributed query engine there. R2 aggregator is there, and then some time series databases that you can use. Just quickly, what are some roadmaps for some of this stuff? So at the query engine, we've got most of the features done right now. We want to add more language support. So we want to add M3QL, which is our own, so it has PROM support today. But we want to add M3QL, which is our own custom query tagged query language, and graphite support as well. We also want to add more time series database support to M3QL so that you can use the query engine against not just M3DB but also Influx and a metric tank and things like that. The aggregator, all the code is there, it works, it's just not in a great spot for open source. There's not much documentation, so we're going to be working on that. M3DB, our time series database, we're currently working on the ability to write data into the past, and that's going to be a pretty important feature because as you create these rules, you also want to backfill, right? Because if you can't backfill, you can't get all the data in the past. It's only from that point onwards. So we want to add the ability to backfill data. And then with automation, we've sort of done a really rudimentary automation of like a subset of our use case, but we actually want to write a proper service that can like talk to both the aggregation tier and the query engine, and hopefully do all of this stuff in an automated fashion. All of this stuff is open source, so please also feel free to contribute as well. Cool. That's all I had. Do we have time for questions?
We can do like one or two.
Sure.
I saw we can go up over there. I can come to you, no problem.
Hi, Richard,
Hey,
Prometheus team. Thanks for a great talk, and also thanks for putting engineering resources against open metrics. You were talking about scaling Prometheus. Did you look at Thanos and/or Cortex for this purpose?
We haven't looked at it deeply. A lot of the logs that we looked at said we are solving this problem of scaling up the Prometheus instances. I just haven't seen the solutions.
Okay, so basically there you could, so with Thanos you could put non-local storage just in object storage. And with Cortex you have the same on the index where you can scale horizontally. So maybe it's worth looking at that.
Perfect, yeah, we'll do.
Okay, one more. I got one right here.
Hi, great talk. I have actually a couple of questions. I wrote it down. What is the highest ingestion rate reached with how many nodes and specs? I mean, CPU, memory, I mean. And how do you handle the metrics cardinality?
Cool, good questions. I think you mean ingestion into the time series database. So pre-aggregation tier, we do about 700 million per second metrics. Of course, that goes all through R2. Post R2, one of our clusters, so overall it does about 30 million writes a second. One cluster does, I think, up to about 7 million writes per second. The cluster is about 50 nodes of I don't want to give you the exact specs, but like of an equivalent of an R2 instance in the AWS type. And what was the second part of the question? Sorry, I forgot.
Metrics cardinality, how you guys handle the cardinality in the metrics?
Yeah, so we actually just take all 3.2 million and dump it into that time series database because it's pretty optimal actually. It has an embedded index and everything. So for that 3.2 million, we just throw it straight into our time series database. That cluster that I was talking about handles about 400 million metrics also.
Let's give it up for Martin.
Cool.